All right. I think we can start. So just to recap, this is where we stopped last time, right? So we start with the Dicke model. I mean, for this part, it's not so relevant. We mapped our spins to auxiliary degrees of freedom to Majorana fermions, right? And then we sort of followed with the standard 2pi procedure to derive the Kadanoff-Bain equations, and one of them we actually derived explicitly, or I think I should say sketch the derivation. I think that would be more clear, right? And so basically, for photons, you need 7 more of those as mid-field equations. And then likewise, for the Majoranas, right? Okay, I'll just show you the end results, kind of. This may be like one of them. So there's a typo in the notes, but that's all right. So for Majoranas, right? So you would have similar equations. So for instance, you would have in a matrix form something like this. So this is the free part, right? Of the so this is if you show the free inverse propagator times, for instance, let's get a Celtic component, so gamma theta is classical prime minus, so then you have the Majorana self-energies. One classical k convolution G K minus H minus phi alpha gamma 1 K. K 0, right? And likewise, I mean, okay. Why not? Let me write that it's one of them, and the other one is, let's say, conjugate this one, so it's easy to see the structure of the remaining one. The classical quantum I k minus phi gamma classical right. And so it's a very similar equation for quantum classical. Like, so again, you can play the same game, right? So with translating this, say, propagators to statistical, right? F means fermions, right? Statistical and spectral functions, right? There is one important, let's say, simplification. And I probably should mention that this thing here, right? So with I am beta equal to 0, omega z, 0, omega z, equal to phi. So this equation is coupled to the mean field, to the photon expectation value of the mean field. So you, as I said, you can do what we did last time and translate these equations to these variables, right? And otherwise, so sigma, no, I use pi, right? So say pi f beta pi rho alpha beta, right? There is one exception, sorry, one important thing, right? Which is that note that so our action is invariant under gauge the two transformation. So I'll quickly. So what I mean by this, so it is invariant under following transformation. So you just take your Majorana fields, right? And add the minus sign. So there is really not much deep about it, right? This is simply, I mean, this essentially simply reflects the fact that our, let's say, degrees of freedom, so these Majorana fermions, right? So they are these auxiliary degrees of freedom that we use to parameterize the spin, right? So to map our spin to these degrees of freedom, right? And so essentially, like, and obviously, right? So for each spin, we had two Majoranas on the same side, right? So essentially, like that's basically the reason why you have this this auxiliary degrees, so this symmetry, right? But what it essentially implies in essence, the important takeaway, it implies that our propagators are diagonal in, say, in real space, right? So in the in the space of, let's say, atomic labels, so diagonal in space. So if you think that I is like, let's say, some labels, not lattice sites, right? So that this means that, yeah, like always, we are diagonal in real space. And I mean, from this, it also immediately follows that so do propagators. So are propagators, they are also diagonal. So this reduces the complexity at all, by a lot. Is there more, right? So let's say, I mean, this will sort of almost reveal the answer. Okay, do you think that we have, do you think that our propagators and self-energies depend on the lattice site I? What? On I. Let's say, so remember we had, so sum of I, let's say sigma I X, right? And let's call this I so that we have a lattice, right? So we have lattice index, I mean, for simplicity. So do we have the remaining dependence on this spatial degree of freedom I?
The system seems to be permutation invariant.
Or let's say, I mean, let's maybe even say in a simpler language, it's homogeneous.
Yeah.
So we have homogeneity,
Yeah,
thereby, so
Because the field do not depend on the site.
precisely, yes.
Field is, but
Thereby, in reality, we don't even depend on this, right? So reality it's even simpler. We have just this. And this, I mean, this is a huge simplification, right? Because instead of having, let's say, if we had full dependence, right? Then we would have n squared, for instance, propagators, right? So n squared equations, I mean, for each propagator, right? So let's say gxy, and then we would have ij, so we would have n squared of gxy, right? Now, because of this, let's say, additional gauge symmetry, we know that, okay, in reality, it's diagonal, right? So it's n. But now we know that, oh, it's actually not even n, 1, 1. So we only have essentially one equation per, let's say, propagator, right? And then again, sort of, we know that there is a symmetry between gxy and gyx, right? So, okay, but we'll come to this second. So, okay. So we have this equation, right, which, as I said, we can rewrite in terms of statistical spectral propagators if you want to. I mean, in principle, you can also, keep working in this classical quantum basis. No one sort of forbids you. I just prefer the classical and statistical, statistical and spectral language if you wish. And finally, we need to supplement this. We have the equation for photonic mean fields. By the way, when I say mean fields, like I don't mean that like it's some mean field approximation. I simply mean that it's expectation value. I know that in certain communities, this like when you say mean field, they assume that you make some mean field approximation. But here I just mean expectation value. So not the 2-point functions, but 1-point functions. Yeah, this is what I mean by mean fields. 1-point functions. Oh, and while I'm writing these equations, here's the question. Why do we not also have equations for 1-point Majorana functions? This, and then here we would have y, z, classical, t, t, and say an exercise show that this is this. Okay, so why don't we have an additional equation for Majorana? So why don't we have something like this?
because we're not changing. It's
No. So, okay, so what is this, right? This is expectation value of phi. For fermions, what is this?
the number.
So what is the expectation value of a thermionic operator?
It's n.
Oh, it's actually 0.
So I'm going to the answer. It's not the number of operators, the fermionic operator.
Yeah. So I mean,
Sorry.
well, okay, no. I mean, I think it's in general. Okay, it's not true, but say, I mean, we have this, right?
No.
So you see, we have this like huge gauge redundancy, right? We have this symmetry. Okay, so summarize. We have equations for the photonic propagators, right? Then we also have equations for the Majorana propagators. And we have the one-point function, equations for the one-point functions, right? So basically, the only thing left to close the system of equation is to specify the self-energies, right? So far it's general, right? But now we need to, let's say, make a choice of let's say diagrams that we take into account, and then compute or express the resulting self-energies in terms of propagators. Once we do this, right, we have a fully closed system of equations, right? But, you know, everything depends only on the 2-point and 1-point functions, and we can solve this, for instance, numerically. Okay. So I can raise this, right? No. So to close the set of Dysons or Cardinal vein, I mean that's just another like name for equations of this type in like non-equilibrium and equilibrium setups. The equations, it is left to specify the self-energies. These sigma and pi, right? Or in other words, specify gamma 2. Remember, there was this part which is the sum of all two-particle irreducible diagrams with respect to rest propagators, all the vacuum ones, and this in the 2pi formalism, which basically gives the name to the formalism, right? Okay, so one option, right? So what is the immediate option? Sort of like what? So in some sense, like we need to expand this in something. Like what is the immediate option? So like perturbation theory, how like usually in what you expand it? So we have
the eigenfunctions of the
No, in the parameter.
yes. Which parameter? So we have the free part, right? And then we have the interaction, which is characterized by the coupling G, right? So one option is function in G. However, so the Dicke model actually offers alternative, so-called, so to say, non-perturbative expansion parameter, right? So, I mean, this is a perturbative expansion parameter, right? Because you do perturbation theory about, let's say, your free theory, right? And then you say that, okay, my interaction is a small perturbation, and then I add it order by order, right? In my interaction. There is, however, an alternative expansion parameter, which is 1/n, right? So we assume that we have many atoms, right? So because if n is large, then 1/n is small, right? And then we have another small parameter which we can use to make an expansion of our 2pi effective equation, right? So, and remember we already at the very beginning, we said that we suspect that 1/n controls, if you wish, the size of the fluctuations, right? So that in the limit of n to infinity, you have this enormously huge collective spin, right? Which essentially self-averages itself and thereby behaves classically, right? So again, think about this law of big numbers, right? In probability theory, this is sort of like the essence of why 1 over n in this case suppresses fluctuations, right? So this alternative parameter essentially offers you say a nice handle to semi-classical approximations, right? So to leading order, you just ignore all corrections in 1 over n. And like more, if you want to add some fluctuations, you add something that is next to leading order in this small parameter, and so on and so forth. And by doing this, you, let's say, build more and more fluctuations, right? So you get less and less Jewish classical, right? So is this clear?
From expansion of G.
In general, it is different, and we will come in a second how, right? Because yes, I mean, yeah, so G, remember, yes, you're absolutely right. G comes with this, right? So you might think, okay, but then because let's say, yeah, I mean, let me draw the diagrams and then we will see. Okay. So and yes, by the way, yes. That's a good starting point, right? So what about let's start with like the classical action test, right? So O. So how does it scale with n? Yes, what is its power?
Against square, because you have a square rule, there's no interaction terms.
What
Linear.
What is n in like let's say for this system, right?
The number of atoms in the cloud.
Yes, or in other words, essentially volume in some sense, right? So it's the system size, the system size.
Yes.
How does your Hamiltonian sort of and all this like thermodynamic quantity scale with the system size?
Extensively.
Yes, or in other words, in this case, I mean, it's linear. So now, what about gamma 2? Right. So now let's introduce the diagrammatic notation. So we call this, because I mean, again, remember that like in the interactions, right, we only had the like the real quantum field, right? So that's like the phi field, so thereby like it's only this one, if you wish, matters. This will be, we will denote. This is yeah, our propagator. And we will denote it I think now, right? But like it's a wave line. By the way, so what does this stand for?
Connected.
Exactly. Connected propagator. Likewise, I mean, I'm being like very explicit here, but remember all the discussion about the IJ and all this, right? This is borders propagator. Okay. Prime. This is just, I mean, again, we will need add, let's say, alpha, beta, right? Quantity really explicit. I think we say understand each other. And then the interaction. This G tilde. And then it has a photon, right? And it is coupled to what?
To the atoms in the cavity.
Yes, but so in terms of Majoranas, how does the interaction term like? So there is pi and there is what? Remember, like the interaction term was G tilde pi times what? So it was originally sigma x, right? I mean, sample. So sigma x translates to what in terms of Majoranas?
The N, right? This N. Eta.
And-
What is eta?
Yeah, yes, eta. So let's make it like this. I mean, again, that's schematically
You have to measure around.
two Majoranas, right? Exactly. So that was it was x, right? So I need something like yz, I guess. Schematic, right? So, but and then diagrammatically, then the two lines, right, are one Majorana, other Majorana, right? So you have two Majoranas coupled to the follow, right? So this is our, let's say, pictorial way of representing the diagrams. So, okay, what is the first diagram? How does it look like? So first of all, can we have something from this? So, like something, yeah, let's say, non-trivial. From just one interaction. So like, let's say, this is what we have. Can we somehow like close it to have a like vacuum diagrams with no external legs?
Only with velocity
Yes.
and no quasi particles in the middle.
No, not just this sort of like, can we somehow like connect the legs such that we have like a nice vacuum diagram, sort of like without external legs or anything?
You could like close them again and then like put those two guys back together, emit a photo, and then expel the two guys again.
But I mean, I only have these two legs and this one leg. But it seems like you're adding more legs. Sort of like, you know, I mean, basically, well, you can try to like close this one, right? But then this one's hanging. So not really, right? So we need to go to the second border, please. So now let's say we have, I'll be kind of suggestive. We have this. Can we connect this such that we have a 2p diagram?
Could connect them directly just getting a photo, or you could create and annihilate those two guys in the middle. Making
Okay, so I can what in the middle?
create and annihilate the two ends. Yeah.
You mean something like this or?
Yes.
No, but like this, we don't have this, right? So the point is, these are all the lines that we have, right? So we take two interaction terms. We have 1, 2, 3, 4, 5, 6 lines, right? We cannot add more in the middle, or we only have this, right? So what are like, how do we connect? So and yeah, basically like there's not much option
Just
left,
the photo going.
right? And then like what about this guys? Yeah. Exactly. So, or let's say, let's redraw it a bit like more in a more natural way. So this is the first diagram. Right? So now let's do some power counting. As it was correctly mentioned, so the interaction comes with 1 over square root of n. The interaction here comes with 1 over square root of n. However, remember that we have, so we know this symmetry, right? That, okay, in reality, it does not depend on I and j and so on. But in substance, what is this, right? So you start with here and end up here, right? And remember that this is, let's say, call it Gij, right? Then, no, so so like when you close this loop, what does it remind you of in terms of matrices? Trace, exactly. So we have a trace, right? A trace over the space of lattice sites, right? Which means we have something like this. And I mean, in this case, actually, they don't even depend on I and j, right? We know this. So we have identical, let's say, objects, something like this, right? I mean, let's say D, right? Schematically. How does this scale with n? No, I mean, it's just one sum.
Okay, yeah, and linear.
It scales with n. So we have 1 over square root of n, 1 over square root of n, and then we have a trace. So this diagram scales as O to the power n to the power of 0,
So
as compared to
if you create another closed diagram with 3 points, it's going to be 0 in the thermodynamic limit in some sense.
so
It's gonna
Well,
have
yeah,
a negative scale.
yeah. So the basically, yeah, I mean, in thermodynamic limit. So in this particular case, also, right? Let's say yeah. So this all these quantum corrections, so say they are suppressed by 1 over n, and say like if we had infinite number of atoms, so this corresponds to one incredibly collective, like huge collective spin. It would behave classically, right? So now, unfortunately, you would have to, I guess, trust me on this. But the claim is, this is the only next to leading order diagram. So this is the only diagram that scales. And maybe as an exercise, show that at next to leading order, there is also only finite number of diagrams. This is, by the way, not very typical. So for instance, in ON pi to the 4 scalar theories, next to leading order requires resumming infinite number of diagrams, or doing something like Hubbard-Satonovich or something like this. But in the Dicke case, both next to leading order and next to leading order contains only finite number of diagrams. So there are only 2 actually diagrams. So what, by the way, I mean, can you maybe guess what can we do? This is like the first part. And we have one more interaction, or like, oh, sorry, two more interaction terms. Can you maybe guess? Oh, I think it's probably a bit too hard if you don't have much, let's say, experience with like playing with such diagrams, but this scales as negatively, so to say, with n. And there is another one. And again, so let's say if you want to do, let's say, if you want to study the Dicke model for small number of atoms, right? And you decide to use 2pi, then yeah, maybe you want to go beyond this approximation and to this, well, I mean, by no means, I don't know, like let's say all the 2PI Dicke model literature, but I've never seen anyone going to next to the extreme. Say so, you could be the first ones.
There's a question.
Yes.
I'm not specifically trying to write final diagrams and those things, but for the little thing I know about graph theory, it's very little. There comes that for each leading order for each next order, you are decreasing by 1 divided by n. It's
Let's say, but this is by definition.
yeah, by definition. But what I'm interested in asking is that you also increases the number of possible diagrams. Like there you have one, there you have two. How do we not know? How do we know that this increasing the number of possible diagrams not go like exponentially or at least a higher order polynomial when there?
Yeah, I see. But also like you yes, but then sort of like, you know, let's say that I see your point. Let's say that here we have one, right? Here we have two. But by the way, let's say that n is 1000, right? So here we have 1 over like 1000. So here we have two, 1 over 1000, right? Let's say that even if they collectively, like, you know, do the same thing, it's still 2, but divided by 1000, right? So you would need 1000 of these diagrams to compensate for this prefactor, right? Now you say, okay, maybe it blows up. But again, still, let's say they would need to essentially all sort of like, you know,
Positively.
yeah, let's say like contribute like in the same way, sort of like collectively, right? Which is like, why would you expect it, right? So that like each of these like topologically different like diagrams and all this, like, why would their effect be, let's say, like why would they not sort of maybe even compete against each other, right? In some sense. Right? Because they really, I mean, they describe different processes, right? I mean, you can kind of like see that these are two different like processes that they describe, right?
Okay, I understand.
So I think, yeah, so it's, let's say it is in principle possible, but I think then for that there should be some like deeper reason behind. Like these things don't happen accidentally. That like, you know, at some, or like you have all of a sudden like exponentially many diagrams of this order, and they all sort of like collectively act such that they like, you know, they can compete with a sort of like, you know, higher order and stuff. There should be some deeper reason that, I mean, otherwise it's
a reasonable ansatz to presume they don't.
yeah, I mean, or yeah, unless again, yes, I would say so.
Is there any way that you can like make some kind of soft coupling, because that G over square root of n is
Yes.
very subjective. It's like very suggestive. Right?
Yeah. I mean, well, I mean, in this case, I would say kind of like no. Well, but I mean, for pi to the 4, yeah, it's basically it's Tichov. Yes. Here, because again, like, but remember, like for Tichov, for like let's say in like in Young-Mills, right, or in like pi to the 4, right? Basically, as I said, you resum all these like diagrams, right? And essentially, basically, you have like this bubble chain, right? And this sort of like so yeah. So like, I think it's natural there to sort of like to think in terms of this like, you know, like Tichov's sort of lines, right? Here, I mean,
Because I mean, like you have Tichov there because you have this kind of double, let's say, planar diagram, right?
yes,
and at the end, because you have matrix fields. But somehow when you put your Majoranas, you put it in pairs. So you have like a matrix field there. So that is the reason why I asked if there is some kind of known way of making like into the hotspotting and maybe some this kind of stuff.
well, I mean, by the way, I mean, in some sense, because remember, it's so the.
So isn't
I mean, since I'm not, let's say, I cannot just like, make 100% clear, but I mean, it sounds. If it's very Hoffish, right? But I mean, again, so I don't like know much about like the, let's say this subject, and I know like these things that I know, I kind of like I don't remember that well. Give a good answer. All right, so in this, for the remaining of this lecture, right? So we will concentrate on the next to leading order approximation. So we concentrate on this diagram. So here's, let's say, so remember we derived these equations, the Catalan-Bayes equations or the Dyson equations in the Cavendish basis, which I consider to be like one of the more convenient ones to derive the structure of the equation. However, I think they're not, this basis is not as suitable for computing self-energies in this diagrams. Why? Because remember, so when you go to Cavendish basis, right, so you have a pi classical, pi quantum, then you would have eta classical, eta quantum, right? So for instance, this interaction, right, it would actually split into well, yeah, I mean, it would split into like many. But if we now denote, let's say, classical means solid line, solid, and then quantum dash, right? So then when you go to this basis, you would have something like, for instance, this, right? Then I think you would even have something really like purely quantum, maybe. Maybe definitely have something like this, and then yeah, I think even so, maybe even this. So the point is, basically, like you multiply the number of possible options, like you multiply the number. I mean, the nice thing is that it will all be expressed in terms of like already not in the contour, right? But I argue that it's better to compute one diagram on the contour and then do the decomposition than work in this basis and have 8 diagrams, right? But sort of, but then yeah, enjoy that we don't have to do the decomposition. I would rather do the decomposition once than don't do it 8 times, right? So that's why we will here, unlike when deriving the equation, we will actually stick to the just contour. So then the analytic expression, of gamma NLO following. So what do we have? I'm going to be very step by step pedantic. So remember, okay, so let's go like way back, right? What was the, let's say, analytic expression for gamma 2? Right, remember it was minus I logarithm and expectation value of this. Yeah, right? So essentially what we are doing here, we are expanding S interaction to the second order, right? So it's sort of NLO, I logarithm 1 plus, right, and then plus, and minus 1/2. Right? Something like this. Okay. And now we expand this again, right? But like, you know, that what is this? The logarithm of 1 plus x is roughly what?
1 of 0 plus x.
Or x. Yeah, it's x. So then here we would have something like, I think I have this interaction squared 2pi, right? Because I mean, this thing, as we agreed, does not contribute. You can't make a 2pi diagram out of this. So we have this. Now remember, our interactions, right? They came with i's. I's by as in I plural, imaginary unit plural. So yeah, we would have something like I g tilde squared, which is minus g squared, right? So all this adds to the following prefactor. So we have minus I half g tilde squared. And then what do we have? We have, again, let's be extremely pedantic. We have sums, I and j, we have c, dt, and yes, let's be very pedantic. It is, we have them, we have t, z, t, then we have, so here it would be t prime, right? And likewise I and j. And then we have j, y t prime, j z t prime, right? And then it's all 2pi. So now we have to contract them, right? So what types of contractions do we have, right? So how do you contract the photon fields? Do they have a choice? This is like what we are doing, right? We're contracting such that then, oh, throwing my shirt on. But yeah, so by contracting, I mean that eventually we have this, for instance, right? So can we have this option? I mean, not really, right? Because remember, we have this symmetry and all this, and overall, the photon Majorana propagator doesn't sound too right. I mean, and again, remember, we have this gauge symmetry, right? So that you can reflect this to minus eta. So then this thing should be 0, right? But basically, the photon fields, they don't really have a choice. They have to be contracted together, right? Now we have two Majorana fields, but then look, see that we contract T with T prime, right? Because otherwise we would have something like this. And this is not 2pi, this is not even 1, right? And it falls apart. So we have to contract Majoranas with different times, right? So let's say this one. Okay, red marker doesn't work. This one. Who do we contract it? I mean, who can we contract it with?
The other y.
With the other, yes. And then this leaves these two ones, right? Is there any other option?
Why cannot you do the cross?
Yeah, why can't? Yeah, sure. Like nothing really forbids us. We can also do
If there has a delta. Oh.
Sorry?
No, I thought
The
there was
delta is the commutation relations, I think. But it's gonna have implications when you compute the correlate. Yeah.
And here also, yes. So yeah, I mean, just again, remember that the commutation relation, right? It essentially, yeah, it makes like for equal times, right? But they're not equal, right? So like you know something about, let's say, I mean, for Majoranas, you know this, right? Let's say alpha, I'm sorry. T prime. Oh, sorry, not T. So for equal times. But here, I mean, they are not even equal, right? So they like, you know, but so yeah, I mean, and also like regardless, so there is nothing that forbids you to compute like the Majorana propagator with opposing, so like with different, say, flavors, right? So different spinning. IZ. So we have two options. Now let's remember one important thing. These are not ordinary numbers, Saint-Grassmans. And then, okay, if anything, no. In this case, it's not even kind of like, you can even think in this case that these are like still sort of like propagators. Oh, sorry, operators. So if it helps you. That's the point is, what is the point? Point is that when you contract this to ones and this to ones, right? You have to first carry this one, eta j y, through eta I z. And this will give you a minus sign because of the anti-commuting nature of fermions, right? So what we end up with are two contributions, which I will.
But can you clarify, because as you said, we know the commutation relations for the same time. There we have the T prime and a T.
But I mean, well, regardless, I mean, like let's say for, yes, but again, let's say that these are Strassmann numbers, right? And they have this, say, property that.
Oh yeah, you're reading the
Yeah.
property. Yeah.
So basically, so like you can simply think that, okay, these are two different Strassmann numbers, right? Because one is I, one is j, so.
Okay. Thank you.
So these are numbers, not operators.
I think it's like it doesn't really like matter too much in this case.
No, because you written that the phi's and the etas are the exact expectation value of some.
Exactly. So like, like whether you think that these are like Grassmann numbers and the expectation value should be understood as in terms of like the path integral and like Grassmann numbers, whether you think that, okay, this is the expectation value as like operators, and then you have some density metrics and then you trace, right? The point of path integral is that it's another way of like, let's say, computing expectation values in particular, right? So like, so you can, I think in this case, it doesn't really matter that much. It's a matter of perspective, I think. All right, so what is the analytic expression then, right? So we have two contributions. This is what we agreed upon. So again, we have our prefactor. Then we have j. Again, let's be very explicit. Then we have this propagator. What is this? Is it D? Is it G?
Which one?
This one.
This is the D.
Yes, D phi phi, T T prime. And then we have R. I will use the advantage of. So we will have the cross. Okay, so I have that's okay. Then okay, that's this. So we have G I Z. And then G Z Y. And then minus, because remember we have to, yes, in this case, minus the other contribution, which I use the blue light, the blue color. We have G, Y, Y, Ij, T prime, G, Z, Z, J, prime. This is our gamma 2, right? So now all we have to do to compute the self-energies is just take the functional derivative with respect to property, right? So we're almost there.
The construction that is the first diagonal with the second. No, you have two constructions there, right? But
Yes.
why the third one not important? Like N, I, N, Y, N, C.
Which one? Sorry. So we,
The first Majorana, that one,
yes.
and the second one, that is.
Because they're at the same time. And this would correspond to the
But
diagram.
Are we different flavors?
Yeah, but still, I mean, this would correspond diagrammatically, right? Remember, we have T prime, right? This would correspond to,
Okay. Yeah,
and this is one pi and no. Okay, so this is what we have. Yes, and now we just need to take the function derivatives. And in this case, I mean, it's relatively simple. Well, I mean, if you're not familiar, maybe not so much, but this is, right, so by definition, 2i, 2, in this case, NLO, right? Sorry. D phi phi, d prime. Right? Simple as that. So, but look, don't forget about all these t prime, like that, this functional derivative and so on. We have something that is linear in something that is linear in d phi phi, right? What would be the result of this derivative? Just basically this, right? And then you would imagine also something like delta functions, right? So that would kill the integral. Yeah, but so it would kill the integration essentially, right? And then what you end up with, so you have two sums, ij, right? But remember that this
Are equal?
sorry?
They are equal?
Yeah, let's say the summation is kind of
Yes, where?
wait, by the way, is it no. Yeah, it's not as simple, right? Because remember we had delta ij, right? So this takes care of one of the sums.
That's why there is only one n.
Exactly. Okay.
But can you clarify again, where is the delta j? I'm sorry.
Delta ij,
Where is it in the expression?
so here,
They are in the G?
yes. Remember we discovered that there is this secret symmetry, right? Which forces these propagators to be diagonal in
Yeah.
and then so you have delta ij times g. And then we also, because we are homogeneous, is this thing, right? So then, okay, yes, and then we only have one n. And then, yeah, as we discussed, so we just, and then it takes care of the integral. And what we are left with is essentially this thing, right? So this is, next to leading order, we now derive the photon self-energy, right? So we have 2i here minus I half here. So they cancel each other.
Yes.
Then we have n from the sum, g tilde squared, and then essentially what's in the bracket evaluated at tt prime. I mean, again, you understand that, like in principle, that like these tt primes are dummy tt primes, right?
Yeah,
Sorry, and then here it should be, of course.
yes.
Sorry. Yes, but then sort of this essentially forces delta functions, and then you have this expression, the g I z dt prime, g z I minus GYY prime DZZ DT. Perfect. Now, in a similar fashion, you can take the derivative with respect to the Majorana propagators, right? I mean, there we will have more options, right? So again, so your Majorana propagator, right? It has this like 3x3 structure, right? So we have pi xx, pi xy, pi xz, pi and okay, since I started, this will finish. Right?
Sure.
And so in each case, you take the derivative with respect to the respective Majorana propagator, right? But now here we see that we only have yz, y. So essentially only have this subblock, right? So we have 4 options, but I mean, I think by now you sort of know how to do this. So let's just give one example. Say yy. So, by the way, yes. So I mean, for the yes, for the fermions, it's a bit more complicated. Let's say the rule is well, it's minus 2i and gamma 2 delta g, and then here it's also like it's kind of so alpha beta beta alpha AB BA IJ JI TT prime.
But in the end, you can just forget the labels of the positions.
Yes, yes. I mean, here I'm just being very general. So here what we have is pi yy, right? We use this rule. We identify that there is only this object that is linear in GYY in this case, so which makes it very simple. You take the derivative with respect to GYY, and then what you end up with is G tilde squared. And by the way, yes, so like this essentially, yes, so essentially, yeah, so like this also check that you don't get this and free vector.
No,
No.
I'm lost now. Sorry.
Because essentially what you're going to get, right? So you take the derivative, I mean, in reality, okay, so you first take the derivative with respect to ij, let's say, right? So here you would take the derivative. Okay, let's make it not with ij, but kl, right? So when you take the derivative with respect to this thing, it gives you delta functions and Kronecker deltas. So it would give you ik and jl, right? If you take the derivative with respect to g k l. And then you have these two Kronecker deltas that take care of this sum. So you don't have any n. We have bottom propagator D, and
It's not the same for when you get rid of the time t and t prime.
yeah, so I mean, like T and T prime essentially here, like, so again, let's say it would be like with tildes, right? And then when taking the derivative, you would have d T tilde minus T, d, and so on. And then sort of like this is how you get take care of the.
Okay.
Then here you have G, Z, Z. Perfect. And I mean, so exercise derive the rest. Perfect. So we're almost there. We really are. So now, I need this. And I need this beat. So now remember that like we decomposed our, I mean, we expressed everything in terms of statistical and spectral functions, right? So we want to do the same here, right? So we have this, let's say, propagators on the contour. Right now, we want to translate them to our statistical and spectral functions. Luckily, yesterday, Aleksandr showed us the trick. I mean, it's not the trick. Let's say the how this decomposition works, right? So the causal structure of G and D reads, right? So this is how you do the decomposition. T prime. Remember, it's this, then minus pi half C T minus T prime. Right, and likewise, you can just like G, right, and then here you have FF. The same thing. And likewise, yeah, so I think but let's write it again. Right, so this, in principle, yeah, so in our case, we don't have the local part, but in principle, you should also take care of it, right? So like if you have a local part, it's in the decomposition. Let's say it has some special place, right? But then pretty similar. Okay, so now the point is, so now it's simple to decompose. Both sigma and pi. Right? Because let's say I'm not gonna show the whole thing, but just to outline, right? So let's say, I mean, here we have two G's, right? And essentially we want to cut, like, let's say we plug this in, right? So we would have something like F, so F fermion, F fermion. I mean, okay, now let me do it like this schematically. So we would have F fermion minus I half signum rho, F fermion minus I half signum rho, right? So now this is what we have, let's say, on the right-hand side, right? And on the left-hand side, we have sigma. So now sigma, again, so sigma has essentially sigma F minus I half signum sigma rho, right? So we need to basically collect everything that comes without like i's and sigmas, signums, right? Essentially, to get sigma F, right? What kind of terms do we have? We have this times this, and this times this. What is the product of, what is the signum x squared? One. Exactly. I mean, probably like you need to be careful if x is equal to 0, but this is sort of like, you know, we are not talking about the local part anymore, right? We are safe. So you have FF, and then you have 1/4 of rho squared, essentially, right? And likewise, you do the same for the sigma rho, right? You just, you have F rho, F, and then you collect everything. What you get. I think this is race. So I shouldn't have. Yeah, we have like 3 minutes, so this is exactly enough to write down the self energies. Just to give you example, we have F. So as discussed, right, we have again prefactor, and then we have FF, right? And then remember we had also minus y, y, z, z, right? So we have now again that. And then we also have, okay, one can show, I mean, the sign was minus, right? So when we multiply minus I, right? So it's I squared, and then divided by 4, so minus 1/4. And then here again, rho y z, f theta prime, rho z y, f. And then here it's plus because this comes from this, right? Which goes with the minus sign. 1/4 prime. And likewise, sigma rho y by. So it's like basically like if you work with this long enough, right? You kind of like you just know that it's f squared minus 1/4 rho squared, and here it's that it's rho f, rho f minus f rho. I'm sorry, it's just like rho f's. So you have rho y z prime f z y prime. Did I do, yeah, y z prime rho then minus y y yeah, that minus rho, sorry, let's do it this y rho that. That's it. And I mean, you do the same decomposition for pies, right? Again, you first compute, of course, other components, you decompose. But now you see we had these equations, the Kadanoff-Bohm equations for propagators, right? Also equations for the one-point functions. And now that we specified our diagrams, we specified our truncation scheme, we specified our approximation, whatever you prefer, we were able to express our self-energy, sort of like the last piece, in terms of the two-point functions. And with this, we have a closed system of equations that we can attempt to solve. And so in the last hour after the coffee break, I will give some details about how you can actually do this, let's say numerically, some caveats and let's say tricks and all this.